The last type of permutation problem that we are going to take a look at will involve ordered sets of arrangements, but there are repetitions of certain objects. So like for instance, if I wanted to rearrange the letters in the word, I don't know, boo. So when I rearrange them, the possible rearrangement, it doesn't matter. I don't see any difference in those two O's. So while order matters, if I, like, for instance, flip-flop these two O's and I write it as like that, you'll be like, it looks the same. So we won't count that separately. But we would count, for instance, this one being a different arrangement and this one being a different arrangement. So there's something different going on here than it was, for instance, if I arrange the letters in the word, for instance, boy. Here it really matters, and I could flip-flop those last two. I could change who is first, so etc. So there is something different going on with the ones where all of the elements are distinct versus the ones where you have objects that are duplicated or repeat. So if you have a set of n objects, that'll be the total number of things that you have, in which n1 of the objects are alike, n2 are alike, and so on. The number of permutations that you have will be equal to n factorial, would be in your numerator, and then in your denominator will be n1 factorial times n2 factorial times through the nr factorial. So that'll be the counts for the duplicate items. And that's kind of a hard formula to maybe see what's going on there. So let's immediately go apply it so we can see what's going on with these counts. So find the number of rearrangements of the letters in the word bubble. Now when I rearrange it, I don't care if it's a valid word. I'm just looking to rearrange the elements. So in the word bubble, I would have 6 elements total. So that's kind of like what this n is acting for. But now I'm going to start keeping track of if I have any repetitions. So in this one, the element of b occurred 3 times. So that's what I'm going to keep track of in my denominator. So my numerator will be 6 factorial. The denominator would be then 3 factorial. It'll be the number of ways it was repeated and then a factorial behind it. So let's clean this up. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. But the 3, 2, 1, I'll just keep that trapped in 3 factorial because downstairs I have a 3 factorial and I will be able to cancel those. Alright, so I just really have 6 times 5 times 4 that I have to plop in my calculator, so there will be 120 different ways of rearranging that. So let's try that again, but with rearranging the letters in the word statistics. Alright, so in this one there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. Now let's take a look at their repetitions. So I'm seeing an S that's repeated 3 times. What else? I'm seeing a T that is repeated 3 times. And it looks like an I that is repeated twice. And that's it. Alright, so upstairs I will have 10 factorial. Downstairs will be the counts for how many times it was repeated and then a factorial. So we'll have a 3 factorial to account for the S, 3 factorial to account for the T, and 2 factorial to account for the I. So on this one, let's see what sort of simplifying I can do. So 10 factorial. And then I'm just going to leave that as a 3 factorial because that'll be able to simplify with this guy out here, and then everybody else I will expand out to kind of see who I can simplify. So this one I'm going to expand out, and that one I'll expand out. Alright, the 3 factorial wipes out that guy. Alright, so who else? So this 3 I can simplify with that 9. This 2 I can simplify into that 10. This 2 I can simplify into that 8. And then 1's in the denominator, that won't affect anything. So In my calculator, I could do 5 times 3 times 4 times 7 times 6 times 5 times 4. So just be very careful when you key all that stuff in terms of who is left behind. So you get 50,400 possible ways of rearranging those letters. So one last example, this one won't involve letters in a word. This one is going to have flags being run up a flagpole, and we're going to be looking at signals. So for the signal, the order will matter. Okay, it's going to be considered or read differently depending on what signal is listed first versus second. So if you want, you can almost think about like Morse code, right? It kind of matters who is first and second in terms of how you interpret the signal that's coming through. So Sally has 4 red flags, 3 green flags, and 2 white flags. So she's going to use all 9 of them to make a signal. So how many signals can she run up? Okay, so there are 9 flags total. So that builds my numerator. That's how many elements you have. And then downstairs will be the count of the repetitions. So there are 4 red flags, there are 3 green flags, and there are 2 white flags. Alright, so let's go ahead and clean this up. Alright, so I always stop my factorial at whatever the largest one I have. So 4 factorial is the largest one down here, so that's where I'm going to stop here. So I had a 4 factorial, and then I will expand out everybody else. Alright, so these 4 factorials can simplify. Let's see, I get some nice simplifying here. The 9 and the 3. This 2 can go into this 8 4 times. And then this 2 goes into this 6 3 times. Alright, so on my calculator, 3 times 4 times 7 times 3 times 5 will give me 1,260 possible signals. Okay, so these ones are going to be ordered arrangements, but they're just a little bit different when you have objects that repeat. So it just adjusts what the denominator is. So this is a formula that you need to have handy to use if you have these kind of repeated elements in your ordered arrangements.